pitch he has. A long time to right field. It's gone. Number 400. There's not about it. There it goes.
Baseball is as popular now as when the National League was formed in 1876. And today's star players pull down salaries that would have been undreamed of 100 years ago. And yet, by one measure of a player's ability, batting average, today's players don't seem to measure up against the great players of the past. Giants like Wee Willie Keeler, who hit .432 in 1897. Hitting .432 means Keeler got a hit 43.2% of the time he was at bat. Players who get a hit more than 40% of the time are thus called .400 hitters, and they're a rare breed. The last player to hit .400 was Ted Williams, who hit .406 in 1941. Are today's players really not as good as the old-timers? In this unit, we'll use statistics to help answer that question. As we often do in statistics, we'll begin by looking at distributions. In this case, distributions of batting averages. We'll see that the overall shape of a distribution can often be displayed as a smooth curve called a density curve. We'll meet a specific kind of density curve called a normal curve and learn why it's so useful. We'll learn a handy rule for making approximate judgments about normal curves. And we'll see how a method called standardizing allows us to compare observations from different normal distributions. Histograms are statistical pictures we use to display the pattern of values taken by a particular variable. This histogram, for instance, displays the distribution of weekly salaries paid to thousands of employees of a large company. The height of each bar represents the number of workers who earn wages in that range. This distribution is skewed to the right. Many employees are paid moderate incomes, while a few receive the very high pay out in the right tail. Also note that while there is definitely an overall pattern here, there is also a lot of irregular detail, which reflects the natural variation in real data. Now, what if all we want to do is examine the overall shape of this distribution? The histogram includes more information than we really need. So we can convert the histogram into another type of statistical picture, a density curve. We just said that the height of the bars in the histogram show how common each value is. But since the columns are of equal width, the area of each column shows this as well. This means that if we draw a smooth line through the tops of the histogram bars, the area under the curve shows how often the values in each region occur. The final step in making a density curve is to set the total area under the curve equal to 1. Now the area of any particular region is equivalent to the percentage of observations falling in that region. For instance, if this area is, say, 0.18, that means 18% of the employees earn salaries in that range. The total area of 1 stands for 100% of the salaries. Because density curves all have area 1 underneath them, they allow us to quickly compare the overall shape of different distributions. For instance, our skewed curve of salaries is quite different from this symmetric density curve. This curve happens to show the distribution of heights of young women. The mean height is 65.5 inches. That's 5 feet 5 1/2. Most women are near this average, while some are either very tall or very short. As people who find themselves in the tails of such a distribution know, life in the statistical outskirts can have its ups and downs. Welcome to the Boston Beanstalks, a unique kind of social club. The Beanstalks are part of a national organization that has over 5,000 members. As local president Brian O'Malley explains, the club is only open to certain people.
The only requirements to join the club are that men must be 6'2" and over, and women 5'10" and over. And it's a social club like any other club, except that this is a club for tall people.
Club members all occupy the extreme right tail of the distribution of people's heights. Just how far above the mean club members stand became visible as our Decisions Through Data producer investigated the situation.
I'm trying to find out what the point of the club is. To socialize with people we can look at eye level. Why did you join?
I joined because I was having a tough time finding somebody my height. I go to clubs and I meet really nice guys, and I'm 6'2", and most of the time they're like 5'9", 5'10", they're usually under 6 feet.
So tall women come to meet tall men, and vice versa. And sometimes it all works out the way it's supposed to.
She was talking to some people that I had met, and we got introduced, we danced, we fell in love, we got married.
Let's take a closer look at the curve describing the heights of young women, including the Beanstalk members. Notice that this curve is shaped like a bell, and it's symmetric, which means both sides of the bell have the same shape. This is typical of a very important family of density curves called normal curves. All normal curves have this characteristic bell shape, but they vary in their spread. Some are skinny and tall, and some are wide and short. Because the normal curves are symmetric, it's easy to see their center. It's right here. That's the median of the distribution, because half the area under the curve is to the left of center, and half is to the right. Remember that half the area under a density curve equals half the observations. What about the mean? Well, it's a good guess that the average of all the observations in a symmetric distribution also lies at its center line. The mean and the median of a normal distribution lie at the same point. How do we denote the mean, or average? Well, if this were a specific set of observations, we would use x bar. But when we're talking about the mean of an ideal distribution, we use another symbol, the Greek letter mu. For example, if we measured the heights in inches of 16 young women in a math class, we could find their mean height. We would call this mean x bar because it is the average not of all young women, but of a select group. If we were talking about the average height of all young women, the ideal distribution, we would use mu instead of x bar. Notice that if we change the mean of a normal curve, we merely shift the curve left or right on the graph. The shape remains the same. Now, what about the spread of normal curves? Since normal curves are exactly symmetric, the standard deviation is the perfect way to describe their spread. In fact, normal curves have the unusual property that they are completely described by just two numbers, the mean, mu, and the standard deviation. The standard deviation of a normal curve is written as the Greek letter sigma, again because it describes an ideal distribution rather than a specific set of data. We can actually locate the standard deviation of a normal curve by eye. Imagine that the normal curve is a snow-covered slope and you're a skier. When you first start out, you're scared because the slope seems to be getting steeper and steeper as you go down. But at a certain point, you start leveling out a bit. You begin to think you'll live after all. It's this point where the curve changes from dropping ever more steeply to dropping ever less steeply. That is exactly one standard deviation from the mean. Of course, that's also true of this point on the other side. Now, we said before that if we change the mean of a normal distribution, we merely slide it back and forth on the horizontal axis without changing its shape. But if we change sigma, the shape does change. Large values for sigma mean large spread in the distribution, so the curve is flat and wide. Small values of sigma mean just the reverse. The distribution clusters tightly around the mean, and so the curve is tall and narrow. Now let's look at the distribution of heights of young women in general. As we saw, this distribution is close to normal with a mean of 65.5 inches. The standard deviation is 2.5 inches. Here's a member of the Boston Beanstalks, out here at 70 inches. As you can tell from the height of the curve at that point, not many women are this tall. But we can be a lot more precise than this. That's because all normal curves, no matter how wide and flat or tall and skinny, are the same when we think in terms of how many standard deviations a value is from the mean. Let's think about that a moment. What we're saying here is that we can use the standard deviation as a kind of yardstick to measure how far away a particular observation lies from the mean. Measuring this way turns out to be very handy If we measure one standard deviation on either side of the mean, then we've marked an area 2 standard deviations wide. And here's the striking fact. For any normal distribution, no matter what shape, this region, 1 standard deviation on either side of the mean, always contains 68% of the observations. If we go out 2 standard deviations on both sides of the mean, we find 95% of the observations. And if we go out yet another standard deviation, to include 3 standard deviations on each side, we include almost the entire distribution, 99.7% of the observations to be exact. This leaves a mere 0.3% in the remaining tails of the curve. This relationship between standard deviation and areas under the normal curve is called the 68, 95, 99.7 rule. Remember those numbers, 68, 95, 99.7. They're a great help in working with normal distributions. Let's use this rule on the curve describing the heights of young women. We said that the mean was 65.5 inches and the standard deviation was 2.5 inches. Now we can immediately tell that about 68% of women are between 63 and 68 inches tall. That's the mean plus or minus 2.5 inches, 1 standard deviation in each direction. Again, using our rule, we know that about 95% of young women are between 60.5 and 70.5 inches tall. Now we can be more precise about where our 70-inch Boston Beanstalk member lies relative to the rest of the population of young women. We just found that 95% of young women are between 60.5 and 70.5 inches. This leaves 2.5% in each tail. Our Beanstalk member is 70 inches tall, and that's here, a little shy of the 70.5 inch point. So we can say that only about 3 or 4% of the population is 70 inches or taller. Placing observations on a normal curve is useful in many situations, including the question of why Major League Baseball players don't hit 400 anymore. Stephen Jay Gould is a professor of biology at Harvard University. He specializes in evolution and is fascinated by species that have become extinct. Maybe that's why he's interested in why another kind of species appears to be extinct, the 400 hitter. Some blame night baseball, or the grueling schedules of today's teams, or a general improvement in pitching. But according to Gould, the problem is more subtle than that.
400 hitting is not a thing. It's not a phenomenon. It's the right tail of a normal distribution of batting averages. What you have to look is at the whole statistical distribution of batting averages. The average batting average for full-time players has been, throughout the last 100 years, about 260. What has happened is that the standard deviation has characteristically and continually decreased in an almost law-like fashion.
We see here the distribution of batting averages in the 1870s. The mean at 260, the standard deviation at 0.049. Over the years, the mean has remained constant, but the standard deviation has steadily decreased. There's less variation between the best and worst hitters. Now that's the statistical way of saying that everyone has gotten better. Pitchers, fielders, and batters.
Now, back in 1900, when the average player was nowhere near as good as they are today, the average batting average was still 260, and that was sitting down here. Ty Cobb and Rogers Hornsby were way up here. They were as close to the limits of human excellence as you could possibly be. And the average player was somewhere down here. So the distribution, the deviation of a Ty Cobb from the average was enormous, and he hit 400. What's happened is that everybody has gotten better. So the average hitter and pitchers moved up here, so to speak. But the batting average is still 260 because they're in balance. A man like Wade Boggs, who is now sitting near that limit of excellence and who would have hit 420, I'm convinced, or more back in 1900, is sitting where Ty Cobb sat. He's sitting near that limit of human excellence. But the average has gotten so much closer to that limit that he can't hit 400 anymore. He's averaging 350 or 360, which is a wonderful average. That's all that's happened. The standard deviation has decreased because the sport has gotten so much better.
In other words, the departure of 400 hitting is not a sign that greatness has gone. In fact, it's a measure of the increase in the skill of the average athlete and of baseball in general. Normal curves allow us to get a clearer picture of just how far the great batters stand above their fellow players. We've seen that all normal distributions are the same when we measure in standard deviations away from the mean. Therefore, using the standard deviation as a yardstick, a measuring unit, enables us to compare observations from different normal distributions. The conversion of a specific value, x, to units of standard deviation is called standardizing. To standardize a value, we subtract the mean, mu, of its distribution and divide by the standard deviation. For instance, let's standardize the batting average of Ty Cobb. His batting average in 1911 was 420, so x is 420. The mean for all players that year, that's mu, was 266, and the standard deviation was .037. Doing the math expresses Cobb's batting average in standard deviations, 4.16. We saw earlier that 99.7% of players fall within 3 standard deviations of the mean. So 4 standard deviations above the mean is extraordinarily high. Now, here are the standardized values for Ted Williams and George Brett in their best years. Notice that George Brett, who hit .390 in 1980, is really in the same league as 2 of the greatest hitters of all time when we standardize the scores. In other words, relative to his peers, Brett is just as great as the heroes of the past. In this unit, we've moved through a series of simplifications, from histograms to density curves, then to normal curves, and finally to standardized measurements that allow comparison of observations from different normal curves. Now, not all data can be pictured using normal curves, but the fact that they work on things as diverse as batting averages and women's heights gives you some idea of the vast range of applications in which normal curves are useful.